Okay, now that we're in the realm of large sample spaces, we're going to talk about permutations, which allow us to find possibilities in large numbers, but specifically when these possibilities include situations where ordering is important. So a permutation is an arrangement built upon the fundamental counting principle. So when order matters, you're going to want to use a permutation. And tomorrow we'll talk about a combination and how that's different than a permutation. But today we'll just focus on permutations and that order is important. So we're going to learn a new formula and play around with it. It uses factorials, so it's pretty straightforward. Some typical examples of permutation type problems: when you have a group of people and you have to choose a president, a vice president, and secretary from a group, or leaders in a group, when you want to rearrange letters and say how many different combinations could you come up with from a certain word, finishers in a race, any situations like that where the order of placement of people is important, then you're going to use a permutation. So here's an example. We have 8 people enter pie contest. How many ways can a blue, red, and white ribbon be awarded? Now, I'm just going to tell you that n is equal to 8, and this other little number is equal to 3, but you don't know what that means yet, but it'll come clear in a little while. Okay, so if we want to solve this problem of 8 people entering a pie contest, how many ways can a blue and red and white ribbon be awarded? Well, we started by making our little, we didn't do a tree, but we made a little structure to help us figure out what the factors might be. So in the very first place winner, there are 8 different people who could become the first place winner. So we put in an 8 for that first slot. And then how many people, if 8 people could have been chosen to get that first slot, but then that person's been assigned, there's only going to be 1 fewer for the next slot. So there's 7 possible people who could be assigned the second place position, or the red ribbon. And then finally there's only going to be 6 people who are available to get the third place ribbon. Now if I take the product of those 3, 8 times 7 times 6, I get 336. So it would be nice if we had some sort of a way of doing this methodically when we're given a certain number of people with a certain number of choices of positions that they might have to hold. And so we come up with, we try to understand a rule. So one way to do that is to look at 8 times 7 times 6, which is, could be rewritten as 8 times 7 times 6 times 4 times 3 times 2 times 1 over 5 times 4 times 3 times 2 times 1. Now why would we add the 5 times 4 times 3 times 2 times 1? Because then you start looking at things that look like factorials. And then we can use some nomenclature with factorials, which is really simple and quick to write. So how could we simplify this? We can see that cancel out the 5, 4, 3, 2, 1, left with the original 8 times 7 times 6 that we had. So one way to write this would be just 8 factorial divided by 5 factorial. That way we get those 5, 4, 3, 2, 1s to cancel out. But a different way of writing 8 factorial over 5 factorial is to say instead 8 factorial over 8 minus 3 factorial. Now where did that 8 come from? Where did that 3 come from? Let's go back to our original problem. We had 8 people in our pie contest with 3 different ways that they could win. So we can generalize. 8 would be n, and 3 is going to be r. And let's look at the definition of a permutation. When a group of objects is arranged in a certain order, the arrangement is called a permutation. The number of permutations of n distinct objects taken r at a time. So in the last one we had 8 people taken 3 at a time, in other words 3 leadership positions. The formula works out to be, and this is the nomenclature, we say the permutation of n comma r, or n choose r, sometimes we say. It's also written out this way, npr, the permutation. And you'll see, if you look on your calculator, have a little button that has an npr on it, and we'll practice that later. Alright, so to go with the problem we had before, the permutation of 8 taken 3 at a time is 8 factorial over 5 factorial, or you could write it 8 capital P 3. That's just another way of writing a permutation. So we did this monopoly problem yesterday in the fundamental counting principle. Let's look at how we consider it now that we understand permutations. So you have 6 different pieces in a monopoly game and 4 people who want them. So how could you calculate the different combinations of pieces that people might have? So using our permutations, we have 6 taken 4 at a time, which is going to be 6 factorial minus 4, 6 over 6 minus 4 factorial. And when you multiply that out, you should get, keep going, sorry, 720 divided by 2, which is 360. That doesn't, yeah, that looks right. Okay, so 360 total combinations. Now remember, we got that yesterday by saying, well, the first person's going to have 6 to choose from, the second person's going to have 5, and the third person's going to have 4, and the fourth person's going to have 3 to choose from, and you multiply those out. So this strategy we are now using in a formulaic way by doing a permutation. So this is the same thing over here. So a new problem, how many ways can 8 people, okay, I'm going to change that because I already did an 8 with 3, and so that's boring, so I'm making it 10. How many ways can 10 people in a race finish first, second, and third? Okay, so you ask yourself, what's the number of elements? Okay, we have 10 people. How many are they taking at a time? 3 at a time. So plug it into our formula. We're going to get 10 factorial over 10 minus 3 factorial, which is 10 factorial over 7 factorial. You can use your calculator. That's basically 10 times 9 times 8, and you'll get 720. Okay, how many ways can the letters in peanut be rearranged? So this is sort of a special case of, you'll see problems where you have to rearrange words, and you can use permutation to do it. The idea is that you have 6 letters, and you actually take them 6 at a time. So let's think about how we would solve this problem using the fundamental counting principle, right? The first letter, if we wanted to rearrange, there's 6 different possibilities for the first letter. But once that first letter is nailed down, there's 5 possibilities for the second letter, and then 4 for the third, etc. Okay? So that becomes a factorial, 6 factorial. How can we write that, though, in permutation form? Well, this is the same thing as the permutation of 6 items, okay, there's 6 letters, taken 6 at a time. And so how would that look in permutation form? So we got 6 factorial over 6 minus 6 factorial. Well, that's kind of weird because 6 minus 6 is 0, and you think, uh-oh, 0 in the denominator. But no, because 0 factorial is defined as 1. So we can say that is 6 factorial over 1, which is 6 factorial or 720. So you can use a permutation to solve problems where you have word arrangements. Now, different way to look at this, though. How many ways can the letters in pop be rearranged? And I've purposely made these in different colors to show you that the red P is distinct from the blue P. And if you do that, then according to our last example, you take the permutation of 3 objects, those are 3 letters, taken 3 at a time, which is 3 factorial. 3 factorial is 6, so you get 6 different possibilities. Now, what if we say instead of having a red P and a blue P, we're just going to have them all be the same? Then we have duplicates. Now how many ways can pop be arranged? Well, there's really only 3 ways. You could have POP, OPP, and PPO, because you have this duplicate of the P's. So you'd have duplication if you were considering these ones over here. So you got OPP here, and you have OPP there, so you can combine those into one arrangement, given that the letters are not considered distinct. So where did you get with this, and how could this relate to a permutation? Well, this is going to be 3 factorial divided by 2 factorial, which is 3. The 3 is the number taken, the total number you're starting with, and then that 2 factorial is the number of repeats that you have. So we have a formula for dealing with arrangements of words that might have repeating letters, and this is what it looks like. You say the number of permutation of n objects of which p are alike and q are alike is n factorial over p factorial q factorial. And so I'm going to give you an example so you can make some sense of that. Find the possible arrangement of the word geometry. Okay, geometry. So how many letters in geometry? We have 1, 2, 3, 4, 5, 6, 7, 8 letters. So that's permutation of 8 letters taken 8 at a time, which is going to be 8 factorial. But we do have 2 e's in there, so we have a repeat. So, according to the formula we had before, that's going to be 8 factorial over 2 factorial because the e's repeat, which works out to be 20,160 different arrangements of the word geometry. Aren't you glad you don't have to make a tree diagram for that? Okay, what about Mississippi? This is kind of a famous permutation problem. So in this case we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. 11 letters, okay? But let's look for repeats. We have the S repeat, and we have 1, 2, 3, 4 of those. So S repeats 4 times. The P repeats twice. The I repeats 1, 2, 3, 4 times. And that's it for our repeats. There's just one M. Okay, so how could we now calculate all the possible combinations of reworking the letters in the word Mississippi? So we say that's going to be 11 factorial divided by, now we put 4 factorial because that's going to be the number of repeats of the letter S. And now we're going to multiply by the number of repeats of the letter P, so 2 factorial goes in the bottom because that's another repeat. And then we have the I repeating 4 times, so we're going to add another 4 factorial in there. And that is your formula for determining all the different ways that Mississippi can be rearranged. So plug it in your calculator, and what do you get? 34,650 different ways to arrange Mississippi. Another kind of special case, we call this a circular permutation. Sometimes they'll say, how many different ways can you arrange somebody sitting around in a circle? Or you might talk about the ways that keys are going to be arranged on a keychain, or beads on a necklace, something that's in a circular format. Okay, so how would you come up with a formula? So one way to think about this is if you have 6 seats, okay, and we wanted to do it the old-fashioned way where we say, all right, how many people can sit in the first seat? Well, if you nail down one person in the first seat, okay, so you have one person in the first seat, then the next seat there are 5 different possibilities, right, if you have 6 people altogether. This is not musical chairs. This is where the number of seats matches the number of people. Okay, so one person gets the first seat, and then 5 people can choose for the second seat. And then after you've selected that one, then 4 for the third, 3, 2, 1. And what you see is that you get a factorial here. But look at the factorial. It's going to be 5 times 4 times 3 times 2 times 1. The factorial in a circular arrangement is 1 less than the number of seats. So in this case, we had 6 seats. It's not 6 factorial, but it's 6 factorial divided by 6, or 5 factorial. Okay, so here's our formula here. If you want to know the permutation of a way people sitting in a circle, you take however many people there are and factorial divided by the number of people, or you can just take the number of people minus 1 and take that as a factorial. So how many ways can a family of 6 sit around a table? Well, n is equal to 6, so we can say the probability permutation is 6 factorial over 6, which is 5 factorial, which is 120 different ways that people can sit around a table. And that concludes our lesson. Okay, please take a few minutes there to do the worksheet. There are 8 questions, and it's mostly just working formulas for permutations and a couple of rearrange the word problems, so it should take you more than 5 minutes. Okay, thanks.